Okay, here we have the inverse, contrapositive, direct proof, and indirect proof. Now this is a bit more difficult. We're going to be, you really got to give some thought. We're going to be getting into the Hinge theorem, which, was discussed in Geometry A generally, but now we're going to get into it specifically, what the Hinge theorem is. And so I've got to kind of make sure I can explain this to you. This is probably going to be a little bit longer here. In addition, you have the concept of a direct and indirect proof. And if you're not real familiar with the inverse and contrapositive of a conditional statement, this is going to take a little while. We're going to go through conditional statements briefly, and then we'll talk about the inverse and the contrapositive. You have a lot of work to fill in, which is good. It'll help you kind of get good at that. And then we're going to talk about indirect proof, and then we'll use it to prove the Hinge theorem and its converse. So let's start by getting into, again, a conditional statement. Every conditional statement is written as if P then Q. It's not always written that way, but that's the common way we describe it. If P then Q. And there are three additional conditional statements associated with it. So we can start with if P then Q. We can do the converse, which is if Q then P. We do the inverse, which is if not P then not Q. And the contrapositive, if not Q then not P. So you're basically going to be reversing P and Q, the order to make the converse. You're going to be negating P and Q to make the inverse, and negating and reversing P and Q to make the contrapositive. So now what's really interesting is that you're gonna be exploring doing this in here, and you just need to be very comfortable with what we mean when we're saying if P then Q. Remember, a conditional statement states that there is some condition that exists. In this case, you can see it here. The if a quadrilateral is a square. So in this case, the quadrilateral is P, right? I mean, if that quadrilateral is a square, this is the part that I would write down as my hypothesis here, or sometimes we call it the condition, right? So the hypothesis is a quadrilateral is a square, okay? And just remember, hypothesis is not an educated guess like it is in science, and it is a condition that must exist in these logic statements here. So, you're going to say, for the hypothesis again, a quadrilateral is a square. There's always a then part to this statement, so then, which only applies if the condition is met. So the quadrilateral is a rectangle. So that would be our conclusion, Q. You'd write down the quadrilateral is a rectangle. So obviously, when we're doing proofs, we're actually trying to prove whether or not this conditional statement is true. And what we always do when we're testing the truth statement of a conditional statement is we have to assume that the hypothesis is true. We start by just assuming it's true. And this is what we call a direct proof. We assume that this is true. Then we use the logic. What does that imply if this is true? And, if a quadrilateral is a square, that would imply that it has all right angles. If it has all right angles, then it would be a rectangle, by definition of a rectangle. So in this case, we could test it with a direct proof, right? What's important is that you understand that concept of testing whether or not something is true. Because what they're going to have you do is they're going to have you test whether or not the statement is true. So make sure you accept first the hypothesis or this condition. If the quadrilateral is a square, then follow the logic and see if the conclusion would be true. Okay? Now, when they ask you to negate it, you would just write down here if a quadrilateral is not a square, right? You're just going to change it. You're going to negate it, so it's not a square. Then the quadrilateral is not a rectangle. So for the inverse, you combine those sentences and write them in here. And then you run the test. So if it's not a square, then it may not have right angles, or it may not have, it could have right angles, but it may not have, all we know for sure is that it doesn't have both right angles and all sides are equilateral. Well, if it doesn't have four congruent sides and it doesn't have four right angles, it's not a square, but it could still be a rectangle, right? Because it could have four right angles, just not have four congruent sides. So, the inverse in this case is not going to be true because it could be a rectangle, even though it's not a square. Okay, so just ruling out that it's not a square does not rule out that it's not a rectangle. So we assume that it's not a square does not mean that it is not a rectangle. Okay, the contrapositive is then where we put this backwards, right? If it is not a rectangle, then it is not a square. So now thinking about that, if it's not a rectangle, what does that mean? So we assume that it's not a rectangle. That means it does not have 4 right angles. Well, then the second part of the contrapositive says, then it is not a square. So is that true? You know, if it doesn't have 4 right angles, then it is not a square. Of course, that's true. We'd have to have 4 right angles for it to be a square, so the contrapositive is true. So you're going to go through doing that for each of these statements. If an integer is even, means that it's not odd, right? It's an even number, then it's divisible by 2. The nots on these would be if it is not even, then it is not divisible by 2, okay? And the inverse is going to be, you know, combination of not P, not Q, and the contrapositive is not Q, then not P. If it's not divisible by 2, then it is not an even integer, or then it is not an even integer. That's right. So you're going to work your way through that, and the same with this polygon 6 sides. You're going to go through this, and then when you're done, you're going to make, and there's another one, a fourth one there about lines intersecting. And then when you're done, you're going to notice that the conditional statement and its inverse, you're going to think, is it always true that if a conditional statement is true that the inverse is also true? Or is it always false? Or is there sometimes no relationship where it could be true and could be false? So you got to answer that question. Look back at all the examples you just did. And then it says, what do you notice about the truth value of a conditional statement, truth value of its contrapositive? And what you should notice here is that when the truth value, or is that when a conditional statement is true, then its contrapositive is also always true. So here we go, proof by contradiction. And in this case, what we're doing is we are assuming the, here we have, let's see, you want us to prove that triangle CHA is not congruent to triangle CTA. So what's going to happen is we're going to assume the opposite. You see what this says? The first line is take the proof statement, whatever they want us to conclude, and we're going to negate it, just like we said not Q, right? We're going to take Q, whatever that was, and we're going to say not Q. So here it is not true that these triangles are congruent. Well, or in this case, they want us to prove that they're not congruent. So here we're going to assume that they are congruent. So in an indirect proof, you start by assuming the opposite of the conclusion, and then you lead yourself through the logic. Well, so then if they are congruent, then, you know, what we should have is we should have that it bisects HT and that they are congruent. But we are given also, there's always this given, and I like to write the given after we've come to a conclusion that CA bisects HT. Notice line 2 and line 4 completely contradict each other. And line 4 is just a follow-up to the logic based on the assumption of line 1. If the assumption in line 1 is that they're congruent, then these sides HA and TA must be congruent by CP/CTC. Therefore, by definition of a bisector, CA must bisect HT. But that's when I would bring up 2 here. Wait a minute. We were told it does not bisect HT. So this is what we call a contradiction. What our assumption led us to was a false statement. And so therefore it must be false. They cannot be congruent because of this contradiction. So we make our final conclusion, which is that actually we know the triangles are not true. We proved it by contradiction by assuming that they were and showing that it could not be. So that's basically what you're going to be doing here. So here you have segment AB is not congruent to segment MB. So this side is not congruent to that side. You're going to start by negating this and assuming it. So you're going to start by assuming, okay, well, if BN is congruent to AN, and think about all the proofs you did in 8.3, then that would mean what? This angle bisector, this ray is an angle bisector, so you'd have an angle, a side, and then this common side. By side, angle, side, these two triangles would have to be congruent. But they're telling us that this angle BRN is not congruent to this angle BRA, and that that would not be possible in two congruent triangles. Because of CP/CTC, these should be congruent also. So given here that they are not congruent, that is a contradiction. Therefore, you've just proven that they cannot be the same. So these are a little tough to do, but you know the key is for you to start by assuming the inverse or the negation of this conclusion here. So here it says prove that BC is greater than EF. So that can be done by first assuming that they're equal and showing that that would lead to a contradiction. Then assume that BC is less than EF, and that will lead that to a contradiction. And since both of these cases can't be true, then it must be greater. And I'm going to let you work through those on your own. And you're going to find, I don't want to make this video too long, but you have the same exact situation here where you're trying to say one angle is greater than the other. So we have to rule out that, you know, we'll start by assuming that they're equal and rule that out, assuming that A is less than D, rule that out, and once you've ruled these two things out, then that must be that it is greater than A is greater than D. So you can work on that. And here you're just really using an application of the Hinge theorem. Now the idea is that with the Hinge theorem, you know, you have two segments that are fixed. So they both drove 35 miles and then 15 miles. So they both drove a total of 50 miles. I like to think of the Hinge theorem like this. If I had turned and driven the last 15 miles at a really narrow angle back, it would have been like bringing myself pretty close back to home, back to Al's Diner where I left from. And you could tell my distance would be a lot narrower on that third leg of this triangle. If the first leg was 35 miles this way, the second leg was 15 miles this way, then the last leg would be, you know, just a little over 20 miles or so this way. On the other hand, if I went 35 miles this way and then I really extended it out, you know, far up that direction, then, you know, obviously I've gone way more than 35 miles to get to my campsite. So, you know, the Hinge theorem makes a lot of sense to me as long as you understand what it's saying. Two legs are fixed in size between these two triangles. Therefore, when I open up an angle, the wider it gets, the more open it gets. That's when you think of the hinge, how it's swinging open, then the longer the third side must be. And as I shut it closed, as I, you know, point that back, the side goes back, and therefore I'm closing this angle here, then this other third side must be shorter, and that's kind of the idea behind it. All right, so using that, here you have two sides that are congruent. You have into two sides, so you have two fixed sides here, and one angle is wider than the other. Therefore, this side, AH, is going to be open wider. It's going to be longer than WP. So it can't be 20 or 21. You know, it's got to be 24. The same thing here. You have two congruent sides. If this one is longer and this one is shorter, then this must be a smaller angle, right? I mean, that's the logic behind that there. So that's pretty much 8.4. Quite a bit of work on that. If you need some help with those proofs, feel free to reach out to me. I'd be happy to help you.